welcome to OneQuantum Africa weekly meetings. My name is Farai Majandu. I am the president for OneQuantum Africa. It is a chapter of OneQuantum, one of the largest community for people who are interested and active in quantum tech. Today, we are very happy to welcome César. César Rodríguez Rosario is a chief scientific officer at Strangeworks. And we are going to hear from him. He's got a few things lined up for the day. And I look forward to his presentation as well. Perhaps let me get a few things out of the way before we have César coming through to share what he has for us today. So most of the times we always have to answer this question about why is quantum important in Africa? Or why should people pay attention to quantum in Africa? I would say, perhaps let me just go through what my thinking pattern is when I look at quantum in Africa. And being an experimental quantum physicist myself, I think now that we are able to control matter at the lowest level, and we are also able to allow these individual particles to, work together, we are opening up a new field altogether, or we are enabling a lot of new technologies. Whilst the first quantum revolution gave us breakthrough technologies like the transistor, solid state lighting, lasers, GPS, and all the beauty of the smartphones that we most of us may be on today, we are now seeing a new wave of technologies that is being enabled by our deeper understanding of quantum physics and also our ability to engineer devices that are based or that follow these laws of quantum mechanics. So these technologies, the beauty of them is they will enable us to solve some problems that we have not been able to handle. And these are problems that are very important in order to move the world forward. For Africa in particular, Africa has got untapped potential in terms of having a talented young population, which is seeking education and skills, and we have got as well vast natural resources that we need to harness in order to drive development in the continent, as well as to drive the development in the world in general. So in order to enable these young people to contribute and create value out of the resources that are in the continent and also deliver to the world, we need to give them skills and education in quantum. So OneQuantum Africa is our effort to make that happen. In general, this is what we are doing at OneQuantum. So we believe in building very strong local communities where people who are active and interested in quantum tech come together so that they can be successful. In order to do that, we build communities locally, which we provide with content and resources. And we also allow these communities or give them access to a global community, global quantum tech community, if you want. We've got mentoring, and for some of you who have been following, you may have realized that even today, I think there's a newsletter that came just a few minutes ago, from Dennis, which indicates that we are now all set and ready to deliver on the promise that we made to deliver mentoring to our communities. We are happy that KISA Technologies has sponsored this program and allowed us to use a platform which is called MentorClick, which allows us to run our mentorship program in a professional way and empower people who are looking at building a career in quantum tech. We also we're curating a database for CVs for people who are looking and who are seeking opportunities in quantum tech. Some of them may be pivoting from other technologies. Some of them may be new and looking for opportunities. They may be graduates, they may be postdocs. So we feel free to send us your CV. We'll make it available to a number of employers whom we are in touch with. We'll look at these databases to find talent. This is something that comes up from our Women in Quantum Summits, where we hosted the Career Fair last time, and even the the Quantum in Africa Summit that we are hosting on May 12 and 13 also has a career fair in order to give opportunities to people in Africa to learn about open opportunities in companies across the world in quantum tech, as well as to learn about how best they can develop themselves so that they can also be employable in quantum. We also have projects that we are working on with our communities. And for these projects, we have partnered with Strangeworks, and it's good that we have got César today. He's going to briefly give us an indication of what their platform is like and what they are looking at and how they are looking to create an impact in the quantum tech ecosystem. So we feel that when we bring our people from the continent together, as well as other experts across the world, we can work on problems that matter and that are relevant to the continent. And we have got a platform to do that. And we thank Strangeworks for giving us access to that platform. Let me also thank our colleagues at the Unitary Fund. They are going to be supporting our summit, which is coming on May 12 and 13. So I want to thank them very much. And they're also bringing what they call the Unitary Hack from the May 14th to May 30th, which is the first open source hackathon with swag and bounties. There's over $2,000 US dollars in bounties for tech issues in quantum open source projects. There's digital swag for all participants that make approved pull requests, PRs, for those who are comfortable with the GitHub lingo. There are also going to be random participants that are going to receive a swag pack in their email. And I'm going to share that link in the chat as we go. So check out this hackathon. It's something that they're encouraging a lot of us in Africa to come through and participate in. As you would be aware, the Unitary Fund has been put in place in order to expand or to improve access to quantum computing resources for everybody across the world, especially those who could be marginalized. Then I talked about the mentorship programs. I'll quickly skip this. I'll share a link to the newsletter that has been released today so that you can also follow and get up-to-date information. You're still able to apply for this mentorship program, whether you want to be a mentor or a mentee. I think we've got 250 people who have already signed up, and we're still counting. And that opportunity is still open for applications. We have got these functional chapters at OneQuantum Africa, which is where we are at today. We have got a startup chapter for those who want to look at the building startups. We've got a Women in Quantum chapter for those who want to promote the development of women in quantum. We've got a chapter in Nepal, which is the roof of the world. We've got a number of chapters that are coming up, but these are the ones that are fully formed. You can connect with me and keep this conversation going at the following links on Twitter, LinkedIn, at Facebook, GitHub, and on my personal website to just check what I'm up to. And it will be great if we keep on, we keep in touch so that we take this conversation forward. To really be a pleasure. Right, now that leaves me to introduce today's presenter, or today's speaker, or today's guest. Today, we are so happy to have Dr. César Rodríguez Rosario, who is the Chief Scientific Officer of Strangeworks, which is a startup that makes the power of quantum computing easily accessible and available to all. Prior to Strangeworks, he worked at Harvard University and Max Planck Institute as a theoretical physicist. He has a PhD in physics from the University of Texas in Austin and a BSc in computer engineering. He is from Puerto Rico, and he says the Puerto Rican natural, so he's a Puerto Rican natural that affirms that the universe is made up of quantum information and his job is to hack reality. He has more than 15 years of experience in quantum computation with over 1,000 citations. He has given talks at Oxford University, MIT, ETH Zurich, Tokyo Tech, Hong Kong University, Fermilab, among many other places. He He dreams of quantum technologies changing the world, and we are so happy to have him here today so that he shares his story. He shares with us how quantum is changing the world from where he comes from. He's got a deep history in quantum, so he told me to encourage you to ask him questions widely about anything in quantum. He has been in this field for very, very long, longer than you can imagine. So yes, you may have ideas about many of the things that you may be wondering. So take that advantage and engage him in a conversation, and you can ask your questions. So this is going to be informal and open. Right, let me introduce next week's speaker. Next week we are going to host Manish Thapa, who's a quantum engineer at IQM. As a teaser for what he's going to share with us, he's going to talk about co-designing quantum computers, which is what they focus on at IQM. So we'll be sharing details as we go about that presentation. Let me also quickly talk about the Creative Destruction Lab. They are calling for applications for their program, which is open. We were trying to find a way that they're going to come and present to this community and share opportunities about how you, as an individual, or if you've got a startup idea in quantum, you can apply and be part of their bootcamp. You can meet other founders. You can have an opportunity to start to form a team or form a company and get a startup. You're going to be mentored by quite accomplished people in the industry. So we'll be sharing details about this as we go. I just wanted to make you aware that there is this call for applications in case you are interested. So yeah, let me stop sharing my screen and invite César to come through and take this forward. So thank you very much, César, and thank you very much, everybody who managed to join us for this meeting and for this conversation. So César, you can take it away. You can share your screen, and we are happy to have you today.
Thank you. Thank you very much, Farai. Yes, so. So, and set things up here properly. All right. Okay. Quantum computing is the biggest revolution in computing since computing started. I really like to think that if we brought Aristotle to this times, he would totally but he would be really puzzled by this quantum logic and all that. So this is like really, really big deal. Quantum computing can be it seems very counterintuitive, but the truth is that reality is made of quantum. Quantum seems strange. This is mostly because our brains evolved to understand zeros and ones. So, zeros, ones, this is how we think. But quantum computing is about using more than just zeros and ones. And good analogy I would like you to think about is, if classical computing is zeros and ones, so it could be like using this exact South Pole and the North Pole. Quantum computing is about using everything else. It's very center right there. And today, I hope that with this short talk, I can introduce you to 5 important questions. What is quantum? Why is quantum? Where is quantum? Who is quantum? And when is quantum? Okay, so what is quantum information? What is quantum computing? Why is it so powerful? Start doing quantum computing. Who should be doing quantum? And when is the right time to start? So to set the stage, I want to sort of tell you where things are right now. When we talk about computing, we talk about high performance computing centers, sensor processing units, FPD, all these 3-letter acronyms. And for me, this and my phone, this is just a classical computer. This is all the same category of things. These are just called classical computers because they use bits. Of course, they're extremely good, right? We're having this fantastic meeting because it's limited for some problems. And there are some problems where the data complexity grows very fast. And the difficulty of calculating that goes even faster than data complexity. And for some of those problems, classical computers are not very suitable for that. This means that they will never catch up because just the exploring is getting harder faster than the computer is getting more powerful. This is where we have quantum computing. Quantum computing it's very new technology. It's deep tech. It's a very early industry, and we're barely starting to see a fraction of the potential. However, we do understand the impact is going to be very large, as in exponentially large, in some very, very. So I hope that today talk with like a little sense of what those are. A lot of people ask me like, so how much faster is quantum computing? And I think that's kind of the wrong question. Asking how much faster is an airplane versus a train, which, you know, airplanes are faster. But if you look at the very first manned flights, you know, Brothers Ride, that kind of thing, those were very, very slow at the time. And if you were talking about just the speed, it would make no sense to do that. The main point about quantum computing is not that it's faster. Of course, it will be much faster than existing computers, but that it takes you places you couldn't go before. It's really about, it really allows you to do computations that are just not possible right now. However, when you start reading about it on the news, you get a lot of nonsense. Like the headlines are sometimes really, really crazy. I'm very surprised always. A good rule of thumb always is, if you do a search and replace and take the word quantum and exchange it for magic, and the article kind of reads the same, then probably the article is very superficial and has no contents. And because of this, there's a lot of hype. And I assure you that quantum computing will be a game changer for a lot of very, very important technologies. Also, it's important to understand what it cannot do. What can it do? What cannot do? To keep like expectations grounded. I believe like this, some of this hype, in fact, it doesn't really help the field, in the sense that it's promising things that we know that quantum computers cannot do. While at the same time, I think quantum computers are going to be groundbreaking and do a lot of things. So I want to focus just on the things they can actually do. Everybody always asks me, so just tell me when quantum computing will happen, and I'll go and I'll check. So there's some people that say that it's never going to happen. I think they've been proven wrong by now, because there's been so many advances that it's very difficult to sustain that position. I think there's some people, so on. Some extremely optimistic people say that we're going to have valuable computers that give us advantages in important problems in 3 years. And I think probably the truth is nobody knows it. Here, I do think that quantum computing is going to be so groundbreaking that we have to start getting ready now. Like, it's kind of a little too late. So this kind of effort of OneQuantum Africa and so on, like this is really like the kind of thing that you should be doing now. Why? Because it's very different than normal programming. It's very different than everything you know. So when this thing happens, because it's going to be exponential, there's going to be a huge need for workforce to contribute to quantum computing. And you cannot just build that in a few weeks. You have to start way, way earlier. So there's a lot of opportunities for people like you guys here. What computing is going to impact? This is an overview of some of the existing algorithms that we know they're going to be very dramatically improvement. I'm sure there's going to be more things discovered. I want to focus first on pharmaceuticals and materials. The reason for that is that it's we expect that we're going to have an impact sooner, but also in later times we're going to have a really dramatic impact. Like, it's going to be very, very transformative. And also because I think these technologies are like the easiest ones to like wrap your head around. Then I'll mention the others. So the reason why I think pharmaceuticals and materials are going to be transformed by this is that all of those are about exploring molecules, developing new molecules with some properties. It could be new medicines to save the world from difficulties. It could be new materials to create better, more efficient solar panels, for example. Fundamentally, quantum computing problems, in the sense that you have a quantum molecule and you have to understand it very, very well to find what is the best candidate for that. The way we do this now is you have a lot of people with lab coats and they mix liquids and so on, and they put glasses and they do a lot of trial and error, of course. And the reason why we do these are problems that are exceedingly difficult to calculate using computers right now. So so if we had a computer that could do that very, very well, we will save a lot of time of trial and error, identifying for these things. So why this is that you fundamentally have start with a quantum problem, like finding the energy of a molecule. Then to simulate it right now, what you do is you try to put it in a classical computer. In this process, you have to do a lot of approximations, and that already had some errors. This molecule, you simulate it for some time, which of course at some point you have to stop. This also propagates some errors, and then you bring back the problem to be a quantum problem, and try to find a solution to this problem. This is a very inefficient method. With a quantum computer, you can take the quantum problem, put it directly into the quantum computer, simulate it directly, boom, you get as much precision as you need, and it scales much, much nicer. So for sure, like I think in the future, a lot of these fields of pharmaceutical, of chemistry, they're gonna be dramatically changed by quantum computers, and a lot of people in those fields, they're not gonna have. There's gonna be less people with lab codes and more people that are quantum developers. Other areas, of course, what's gonna be impact is areas of optimization, finance, logistics. These are all very related problems that quantum computer is particularly suited as some algorithms that are going to be very, very promising to make things more efficient. Similarly, machine learning, data science, and search, we're gonna have a really, really huge impact in those. And also cryptography. Cryptography is going to be dramatically transformed. Quantum technologies allows for privacy that's way more secure than anything that exists. So that with quantum internet, we're gonna be able to secure data way, way better, and it's gonna be very dramatic. With that said, I wanna give you a little overview of the whole quantum industry. And for this, if you look at some pictures of quantum computers, you will find on Google like images like this. This is Google, Rigetti, D-Wave, and IBM, I think. And they look fantastic. I think they look like a steampunk thing, like with like a chandelier. I think they're just beautiful things. However, it's a little funny because this is not the computer itself. This is the cooling mechanism for the computer. So it will be a little bit like, imagine somebody asks you to show a picture of your microprocessor, and instead you show a picture of the fan the computer has to cool it. This is a little bit like that. But you can really, just from looking at this picture, you really get a sense of the difficulty of why building a quantum computer is so difficult. All those things you see coming down, they seem very crowded. This is the cooling mechanism. And this is like trying to do different stages of cooling better and better. And the limiting factor is how many of these cooling pipes you can actually couple to the chip. It is really like, this is really the limiting factor. It's an engineering feat to do this refrigeration. We need to cool quantum computers to extremely low temperatures because although our reality is quantum, quantum information itself is very, very fragile. So and then you end up just with a really expensive and bad classical computer in the end, essentially. So to take advantage of this quantum reality, you really have to cool it very close to absolute zero. This is a challenge, and this is the main challenge we have now in the industry. Nobody has figured out a really good way to do that scales to anything that you need. So for this, I want you to think of three main areas that we need to do to have such a scalable quantum computer. One is the number of qubits. You want a computer that has a lot of qubits. That makes sense, right? Like more qubits, bigger problems that you can calculate. When you look at the news, you will see often that this is the thing they mentioned, the number of qubits. However, qubits alone are kind of like a useless number. Like for example, you and I were made of quantum information too, and we have more than 10 to the 23 qubits. So in some way, we're way bigger than any quantum computer right now, but we're not quantum computers. The reason is because our qubits are not properly connected to do the calculations. It's just they just too disjointed. So this is something to keep in mind. That it's just when you see an article that just mentions the number of qubits, that's meaningless. The connectivity is essential because if the qubits are not connected, you cannot do computations. And the last variable that you have to consider is the reliability. These qubits have to be very, very good, and the operations you do on the qubits should be also very reliable. Otherwise, you end up with a lot of noise that just kills the computation. You need all three to be very good. You need a lot of qubits to be able to connect them well enough and to really trust the operations on them. no matter what any of the hardware providers tell you, nobody has figured out how to do this. That is the absolute truth. Nobody knows what is the correct way. We do think that somebody will find a way that will be scalable, and then we will have good projections about when is quantum going to be economically feasible, in the sense that people are going to make money just of running things on a quantum computer. Until then, right now, what all the companies are doing is that they cannot do all three of them, so they're doing compromises. They're doing very, very smart compromises, improving them all the time. So some of the simple compromises is, for example, if you have many qubits and some of them are not connected, but maybe they're connected to a third one, you can use the third one to pass this quantum information. For example, so there's like, it's a way to sacrifice one qubit to ensure things are connected. Other things is, if your qubits are not very, very reliable, you can use more qubits to support that qubit. And together, they might make a more reliable qubit, essentially. It's like a team effort. But of course, that costs you the number of qubits. And you can play games like this. And each of the companies, they are betting on different strategies precisely to do this. That's really what they're doing. They just want to make sure that they want to see if there's a path to find something that's scalable. And they're taking different routes for this, different technologies, different hardwares, all with this in mind. So for a visual image, I want you to think of these human towers here that you have. You can see they have different numbers of people. They're differently connected. Some seem more reliable than others and so on. But right now, none of them seem like they have a scalable thing that you could imagine them being 100 layers tall. Like this is clearly, we're still not there yet. To complicate things further on the industry, we have a lot of programming languages. All these programming languages are very, very early. This is just a few of them. There's a lot more stuff. I just couldn't put every logo here. These are some of the most popular ones, some of the bigger ones. And what I want you to think about is that this CASM here, for example, CASM is to remind you of an assembly language. It's not quite an assembly language, actually. It's more like logic description language. But that's what it should remind you. And this one's here, Qiskit, Shirk, Forest, and BlueCat, they are Python-based to write this assembly language. And they have a lot of additional tooling to do this. So if you're familiar with Python, these ones will seem like very easy. But this also suggests that these are since they just used to write some simple assembly language, that you have to have a lot of physics understanding. Right now, since the computers are so bad, it does make sense to work at a level, you're very close to the hardware. So these are very valuable languages. But at the same time, they're changing very, very fast. So if you look at some of them on the web pages of some of them, they say right away that the language will break compatibility. And this happens all the time. If you go try to run a Qiskit example, I am sure you will find out that they don't work in current Qiskit and there's errors and so on. This is just part of the challenge of this being such an early technology. Not even the programming languages are mature. Then you have some higher level languages like Project Q and Q#. And the benefits of that is that they're much easier to program. And of course, the drawbacks are that they're a bit more disconnected from the hardware. So a lot of the optimization and things that you really squeeze out the little bit we have of hardware. Then you have higher level programming languages like Penny Lane that are very focused on machine learning and big things. And you have other ones that are like they're focused for other kinds of hardware like D-Waves Ocean that works on their annealers. And there's a lot more stuff, by the way. This is like a whole world. If you ask me which one is the best, I will answer you that none of them are the best. They're all good and bad in different ways. And we are at a stage that they all keep changing, they all keep maturing, and that is fine. This is perfectly fine. What I want you guys to think about is we're in an exploratory stage, and you guys should explore these languages. That's really what makes sense in this technology. And it will be that you like one now for some things, and in 6 months, you will like another one better because they are maturing very exciting, I think. But we are really at this evaluation stage. But because of this, quantum computing has a big problem, which is there's a lot of barriers to entry. There's limited access. This is something that Farai already mentioned, that it's hard to get quantum computers and so on. Simulators will only take you so far. The other one is there's no quantum workforce. You guys are here because you're trying to solve that problem, which I love. And the other one is very long term. And this is not like a trip to Puerto Rico, it's a trip to Mars. It's a very long-term thing, and that is fine. And what I always tell people is that if you do not join quantum computing industry because you think the quantum computers are gonna make value next year, join it because you want to build a thing that will make value in the future. That's really what the correct reason to be there now. Like, you want to be part of building. We're not at the stage that the value has come. We are building towards that. And the other side that's very difficult is that it's just all very confusing. This is, I told you about hardware and software and how to put this together. You need a lot of expertise, and it is very, very difficult to find a good entry point. Of course, quantum computing in itself, it's very counterintuitive. So there's like even more things. However, I do think that by having a really broad community of developers, such as you guys, trying things out, this is what's going to help the industry mature. It is not that some expert is going to say, by the way, we should use this hardware and this software. That makes no sense. That has never happened in the history of computing. What will happen is we're going to have developers using things. They're going to find what's valuable, what they find useful, and that's what those are going to be using. So to answer those questions, at us at Strangeworks, we built an open source community that we call quantumcomputing.com, and I encourage every one of you to join and tell your friends about it. Really sign up to quantumcomputing.com. I will give you a quick demo of what quantumcomputing.com is. Yeah. So this is quantumcomputing.com. Let me show you here my account. Okay. This is quantumcomputing.com. You can see I have an account here. If you create your own account, you will have, so I have quantumcomputing.com/César, for example, with you can see my profile here. Quantumcomputing.com/César. You can have quantumcomputing.com/OneQuantum Africa, all those things. You can create a post. I will show you how the post look like here. You can create posts. So this is supposed to be like a Medium kind of thing, but it also has some equations. I usually write it LaTeX very well. However, the most important thing is not that you can write, you can blog posts, is that you can code in the library, and without installing anything. So we take care of all the compatibility headaches for you guys. And I just want to show you like the kind of projects that we support here. So if you want to create a project here, you can create one. You can import from GitHub, from any Git repository, so you can import them in. You can go to a library and use examples that we have, or you can create one from scratch. Let me show you what we support here. So if you're gonna create a project, you can choose one of all these. You can have a blank file, some basic Python, Jupyter notebooks, OpenCasm, and we have all these other languages as well supported. So this is stuff that you can do. You can click on one and really start coding right away. You see, here's some basic code that you can edit and so on. You can run the code in the browser without any installation. And congratulations, you just ran your first quantum circuit. You see, this was building Chasm, and it generated a quantum circuit to create entanglement. And you can even see the outputs of the entanglement when it was. Also, we have a library of code. This is ever growing. We have a lot of very good examples of things of basics of quantum. It's a great place to start learning. And you can see we have the basics of a qubit and all that. And you can run code and play with it and so on. I encourage all of you guys to start playing with this. Go create some code, uncomment some lines, and run some code, and just get started with quantum computing. Also, as you guys create content, we would love to partner with you guys to support it and add it to our library. Creating quality content benefits everybody. So when you come up with cool things, please let us know. Submit it to a library so we can add it. We have already done this with other partners, with the idea that this is an open source community. Of course, you own your code. You can do whatever you want with it. But if you want to share it, we're super happy to support you on that. And there's a lot of, we also have hardware support that's going to be coming. This is a list of partners. So you see, if you want to play with hardware, we're gonna have a lot of optionalities for that as well. And again, I encourage you to go look at the library. We have a lot of excellent examples to get started, such that you can use this as a learning opportunity for that. Are there any questions about quantumcomputing.com?
Okay, thank you very much for that, César.
I'm still not done with the seminar, but yeah, I just wanted to take a little break and ask questions if there were questions.
Good. Yeah. Sounds good. It's okay.
Okay, well, if not, then I'll continue to the next part of the slide, which is just a quick overview of the power of quantum computing. So as I said before, quantum computing uses qubit, it doesn't use bits, and it seems very, very counterintuitive. Although the world is built of quantum information, our brains evolved to understand classical information. The way I like to think about it is our brains evolved to think about saber-toothed cats, not Schrodinger's cat. So stereo and counterintuitive, it's kind of our fault as humans. It's not the fault of reality. We shouldn't blame reality for that. But I want to give you a little analogy that you can keep in the back of your head every time you feel like something in quantum feels a little bit off. In the end, to really internalize quantum, you have to program or do the mathematics so you understand really what's going on that way. But when the intuition is bothering you, please think of this example. And it is analogous to having a 3D object represented in a 2D plane, a little bit like a piece of paper. So when you try to do that, maybe it's going to be incomplete always. So for example, I have this wireframe here that depending on how you look at it, it might look like a box, but it might also look like a corner. And which one is encoded here? It's kind of both. It is really both in it. And so, however, sometimes your brain looks more, sees one or the other. It seems like a little inconsistent. And this is because this is, when we are looking at it, this is an incomplete representation. That's really what it is. If you had it in 3 dimensions, there will be no question about what's happening here. And this is analogous to the quantum information, the qubit. When we look at it, we only see the probabilities of it becoming a 1 or a 0. So we only see it as a bit. And this is an incomplete representation. This is why it's very off. But quantum superposition, of course, is the core concept of what makes quantum so special and what makes quantum so powerful. So with that said, I want to sort of introduce the power of OneQuantum algorithm. So to give you to set up the stage for this, I'm gonna give you first a classical problem, and the problem is the following: you go to the bar and you're walking out of the bathroom and you realize that maybe you had 1 beer too many, and you're looking for your friend at the bar and you cannot see very well because you had a beer too many, and you just decide to walk straight to the center of the bar, and you're stumbling and maybe moving a little funny. And then you got a little too close to one person and you stare at them. It's not your friend. Left, and you look at the other person. It's not your friend. So then you forgot you already bothered this person. You step here and you look again, and it's not your friend. And you keep doing this until you find your friend. That's one option. But most likely, they call security on you and ask you to please leave because you're bothering everybody. And although this drunken behavior is very, very complex, we can model this mathematically. The mathematical way to model this will be to use randomness. So instead of thinking about the drunk and all that, coin, and this coin, if it's heads, you take a step to the left, and if it's tails, you take a step to the right. And although at every step is random, and you can simulate it like this, you will get some structure on this behavior. And it looks like the following. Imagine that you go one day to the bar, and this is the drunken walk that you take. The security guy sees you. This is the security guy here, and he finds you in this spot after a certain number of steps. Then the next day, the security guy finds you in a different place. And this security guy, he was a physicist by day. This was his night job, working at this bar. And of course, he's just gonna keep a tally, keep a note of where he finds you every day after he's been called. So after he does that, so after many, many days, he has some good understanding of your drunken behavior. And there are two things he can conclude. Is that one, you have a drinking problem, and two, that it follows this Bell distribution. And I can show you here. Let's see how this looks here. So this is I'm going to show you here with many of these like metal balls here exactly how this works. And you see it approximates a Bell distribution here. There we go. And this Bell distribution, of course, is very common in statistics, standardized testing, a lot of things in physics. The thing that I want you to think about is the fatness of this curve. The fatness. And the fatness tells you, like, the drunk is more likely, since he always starts walking to the center, it's more likely to find him at the center, close to the center. But the more time that passes, the more steps the drunk has taken, he might be able to it's more likely to wander off to the sides. And this fatness of this curve measures that, and this is known as the standard deviation. So, and it's square root of n. So if the drunk has taken 9 steps, the fatness, the spread, is gonna be like 3 because that's a square root of 9. And if the drunk has taken 100 steps, then the spread is gonna be 10 because the square root of 100 is 10, and so on and so forth. So you get the sense that the more steps he takes, the harder it will be for security to find him because he might have wandered off further and further. Okay, so that was the classical drunk. Let's get quantum drunk.
Sorry, César. I think we had end up. I think that was Rishi. Perhaps you could come through if you don't mind.
Sorry. Oh, sorry.
I think Rishi had his hand up. I'm sure I wanted to ask something about what you were talking about just now.
So I cannot see you. So yes, can you ask the question? Yes.
No, sorry. That was not a hand up. That was a clapping reaction. It was the toy model of the Bell distribution. But yeah, sorry for the interruption.
All right. Okay. Perfect.
No worries. That's okay.
Okay, good. So let's get quantum drunk. So we're gonna do the same thing, but instead of using a coin, we're gonna use a quantum coin. So instead of tails and heads, we're gonna use a qubit. So you allow for the coin to be in superpositions. And this means that the drunk will also be in superpositions. The drunk will go to both at the same time, having quantum interference with himself. This is gonna be the quantum walk. So this drunk, the behavior is gonna be like this. At every step, the drunk takes both directions simultaneously in a superposition, and then again and again and again, and interferes with himself. But when the security guy comes to find him, he will only find him at one place. Say another and another and another. But what is crucial is that the security guy, that's a physicist, he starts to notice that this does not follow the same distribution. The quantum drunk behaves fundamentally different than the classical drunk. And if you're gonna have one image that you walk out from this seminar, it should be this one. When the classical drunk behaves like a bell curve, the quantum drunk behaves like this. He has these fangs, like think of them as like vampire fangs or something. And while the classical drunk tends to be closer to the center, you can see the quantum drunk, sometimes it could be close to the center, but there's some low probability. It tends to be more to the sides. And this is really, really different behavior. And finally, the fatness of the curve is very different. While the classical drunk was square root of n, the quantum drunk is n. That means that he's quadratically times more farther away from the center. This means that it is much harder, it's quadratically harder to find the quantum drunk just squeezes out and spreads out more than the classical drunk. And this is very crucial to the power of quantum computers. Quantum computers can always do that. They can always be quadratically better at anything because of this different distribution of the squeezing. However, if quantum computers did just that, they will be interesting, but they will not be like the groundbreaking thing that we think they are. And I will show you how you can use this for specific problems with specific structures to do more than just quadratically better. So let's put the drunks in a labyrinth. We have this kind of labyrinth, and we send this the classical drunk to find the exit. And yep, he found the exit. Congratulations. Then we send the quantum drunk. He also finds the exit. Nothing very surprising there so far. This is a very special labyrinth, as you can see, because it really, every time it spreads into 2, But then in the middle, it's all scrambled. This is known as a glue tree. This labyrinth has a specific structure, and the scrambling happens only in the middle. Now, let's send more drunks to see how they do. So when you send more drunks, you start to see that, they start making it to the end, but some quantum drunks take a little bit, some of the classical drunks take longer, just a little bit longer, a little more. They're just a little confused here, a bit more. And when we send more drunks, this become more and more dramatic. Some, like, they take longer, the classical drunks always. And this is because the quantum drunk, it spreads out more and it can escape this labyrinth, this part in the middle that is it's all random. And so this gives it a benefit to find the exit and get unstuck. And finally, if you do this with enough drunks, you can show that the quantum drunk for this kind of labyrinth, it is exponentially better than the classical drunk. And this is because of this idea that you have a problem with some structure. It is the labyrinth in this part here. And you have the spread of the quantum drunk, and you just optimize this for this problem to get an exponential advantage. You take the quadratic advantage and turn it into exponential. This is true for a lot of quantum problems, by the way. You always have this quadratic advantage, but then you can do a bit more to make it exponentially better for some problems. Some problems you cannot do exponentially, but if you match the idea of coming up with new quantum algorithms is really to match these difficult problems to clever solutions to exploit this quantum behavior to do better. It is always about the structure. The structure matters a lot. This is why quantum computers are not magical and can do everything. But this is how they all work. And of course, again,
okay. Sorry, César. Now I think we have a hand up from Rishi.
Okay.
Hey, now, yeah. So can you tell me, if I want to Google more about this kind of stuff, what are the keywords that I should Google, basically?
Quantum Walks, if you go to quantumcomputing.com, you will find a hands-on coding example of quantum as well. I thought that would be a really good resource in our life.
Sorry, we missed that. The last word.
If you go to quantumcomputing.com, there are our open source community, you will find posts about exactly this example with the same images and code, perfect. And also references that are good to start. Yeah.
Awesome. Thanks, César.
Okay. Any other questions? Okay. So just to wrap things up, I mentioned that we had this public community that I really encourage all of you guys to go learn there, contribute, create posts. We will add them to the library very happily, so you get more visibility and more credit for your share it. We are happy to help you. This is intended to be an open source community for people like you that want to get started, that want to grow this field. Of course, in Strangeworks, we also have the enterprise tools that are, for big places that want to do like very serious development, organizational management, and so on. This is where a company makes the money. And then, and to wrap things up, I was asking you who will do quantum development, and I want you to think of this picture. This is the ENIAC. This is the first computer, of course, and this was very early. This was the earliest days of computing, and it was very difficult to get access to this thing. Developers have to beg for access, and a lot of people just were not allowed to use it. Imagine how much faster computer would have developed if we already had the internet before the computer, where you could have a community of people testing this early hardware, improving it, suggesting ways to make it better, and coming up with solutions for that. This is where we are now, and these developers are you guys. This is really what I'm encouraging you to come join and be part of this. This is the time for that. So when is quantum? Quantum is now, and please get in touch with me on Twitter or with our Strangeworks Twitters, and I'm always very happy to when people connect and give us feedback. Thank you very much.
Thank you very much, César. That was a great presentation. Very, full of information, simplified, and obviously the graphics are we're killing it. So thanks for that. I guess, yeah, we are opening the floor for questions. If you guys have got any questions about anything quantum, like you heard, quantum is now. So yeah, come through. If you've got anything that you want to ask, it's your opportunity to, to get through to César and find out what he thinks about stuff. Awesome. So anyway, while that is happening, I'll ask you something, César. I'm always getting very difficult questions from the community, especially young people who I sometimes encourage to come and get started in quantum. So somebody would ask and say, what is the instant benefit of joining quantum tech now? So young people always want quick results. They're impatient. How would you respond to that?
Well, because it makes you cooler. That's that is the instant benefit. Quantum is really cool, of course. Instantly, of course, like it's a growing industry. So if you have the skills, you can find very good jobs. The main thing is that it's just a thrilling industry, and that's impossible. I don't think anything is going as that's gonna be so changing, and it's like so puzzling and fun. So I think that will be definitely like. You want to grow quantum, you're excited about it. That excitement is absolutely the main benefit right now for why you should join this industry.
Okay. Are there any questions from the community? Okay. So anyway, I've got a few questions myself. So I'll keep on asking until somebody comes through or until mine are done. So for people who are not in physics, and who are scared of physics, what would you say to them to encourage them to get started? Because they may understand it's very cool, but may still be afraid that with what the history of physics that they know doesn't perhaps get them encouraged. What would you say? Is it for certain people who've got certain capabilities? Can anybody get started?
I think in the quantum industry we need the same kind of skill sets that you will need in any software engineer and software hardware, all those things. So this is the main thing about quantum is we're trying to take it from engineering, and we need everybody to work. If I would say if even if it sounds difficult, if you're thrilled by it, you should do it. This is like an excellent reason to do it. That to be thrilled by it. You don't have to be a quantum physicist like me to work on this industry. But of course, we have people that are designers, as you could see in my slide. We have people that are engineers. We need the same thing that you need for any mature software computing industry. We need all that plus more. For quantum, you need many skills coming together with different levels of expertise on different things. And you should be excited about physics for sure. And if it's hard, that's fine. Your skills you're gonna play to your strength of on your skills, the skills you bring.
Okay, sounds good. Do we have anybody who's got a question for César? Or else I was going to say to you, César, we for problems that are relevant to Africa, which could be perhaps around drug discovery, optimization, and all that, how would you advise us to come together on quantumcomputing.com and forge ties, put heads and hands together and build something? How does that look like on the quantumcomputing.com platform?
Yes,
so that
there we made sure to populate it with some of the stereotypical examples of quantum problems. There's some that are, for example, an optimization of medicine distribution, for example. This is a logistics problem. It's like you have limited medicines. How do you spread it around so people have access to it? Of course, although the quantum solution for this problem might be very technical, this problem can be easily mapped to pizza delivery or a lot of other logistical problems. And this part of transforming the problem, this is something that this is not the job of a quantum physicist. This is the job of people that have expertise on the needs of why the problems are. This is really, you have to be an expert on the problem. So what I advise you to do is try to get some understanding of the problems, so some of the algorithms that quantum is good at, and then take those that you have and create the layer on top such that it actually tries to address the specific needs that you think might be relevant for your interest and your community. With that said, you can collaborate in teams for free in quantumcomputing.com. So you can have many people working on this code, and you can have demos that you can share. You can put like a link on Twitter, and that anybody that has this link and joins the community, they can run it as well. So this is really a good place to showcase your understanding that you're applying quantum software to interesting problems, and from there on, like, just follow your interest.
Sounds good. Perhaps my last question would be, can people come there who are interested in education in quantum, come there, build tutorials, share them? How does that look like?
Yes, so we have a list of resources there. And also, if you find more interesting stuff, you can also create your own post. We will feature the good ones, of course. We want this to be thriving resource. Where you can also use it to promote your own work and such. And we want this to be a growing community of people that are learning from each other, sharing resources, sharing code, sharing good tutorials, and make it easier for people to do that without all the headaches of installing all the software and so on. Yeah.
Sounds good. I think I'm okay. I'm done with the questions that I had. If there are no other questions,
yes,
Abdul, yes, you can come through.
Yes, thank you very much, Cesar. It was such an amazing presentation, because I believe it's like the most let me just put it right here, the most impressive presentation I have ever seen in quantum, because you were actually, like, for attendees who are not actually specialized in let's say in relative fields to quantum computing, they would find this presentation as a very big startup for their careers in quantum, since you're actually talking about quantum, but you're not mentioning a lot of physics. We all know, we all agree that physics is really important in quantum computing, but I believe that the most important thing that communities should be working on right now is how to push the software developers into quantum. I believe the quantum software awareness is the most important thing that as African communities all over the world, the communities should be really focusing on what you are really doing right now, because this is the closing gap era between the physics that we all know about quantum, which is very complicated for some people, and the simplicity in software development for some others. But they actually don't know that you don't really know to know a lot of physics, a lot of quantum computing, just to enter this era. That's all about my quick commentary. Thank you very much, Cesar.
Yeah, thank you very much. And something I want to add is that those ENIAC days, so the first computer, people had to be electrical engineers to program computers. But we are getting to the point that you don't need to do that. You can just use coding, right? You don't need to know anything about how many volts is a bit represented or something. You can just program. And I think it's the same with quantum computing, that you can learn all the math by just doing the code, because the computer does it for you, right? And so you can use, I think it's valid to learn quantum computing by coding. And I encourage everybody to do that.
Sounds good. Perhaps one quick last one. What has surprised you about the quantum industry, how it has been unfolding from the time when you started in the field to where we are now? What are the surprises, things that you didn't expect were going to happen?
Yeah, so of course, the proliferation of interest of many quantum startups trying to focus on different places, and companies there. This is really thrilling to see all the hardware companies coming up with new solutions, the different improvements and advances that they're doing. If you have asked me 5 years ago, that would have been hard to guess that it was going to be so rich. And this was a big surprise, and it makes it very exciting.
Sounds good. So Saha says, thank you. Says quantumcomputing.com is a great platform. Indeed, I've already started using it to collaborate on projects, and good luck with everything that you guys are putting in place for the community. I think there's Ishmael. Ishmael has raised his hand. Yes, Ishmael, you can come through.
Hi, César.
Hi.
Yeah, my name is Ishmael. I'm from Zimbabwe in Harare. At the moment, I'm just a quantum enthusiast. I'm just looking at how it can be applied in Africa and in general, and in Zimbabwe in particular. My question is on startups. You've mentioned that in your experience so far, you've seen some startups coming in to play a role in quantum. Can you explain a bit more on the kind of areas those particular startups are focusing on?
Yes, so there's a lot of startups that are focused on hardware. They're creating new ways to make quantum computers. This is one big, very important category. There's of course software startups. These are mostly they have always a lot of physicists usually, and they are very well trained for some specific applications of quantum computing, and they're really optimizing. They're doing software libraries for people to do this. And then you have the third category, is companies like Strangeworks, which is like we're focusing on the software engineering to make it easier for other people to do quantum. So this is like more classical software startup. It just happens to be that we're in the field of quantum computing. So these are like three broad categories of where startups is happening. Of course, there's a lot of diversity within them, and some are big, some are very big, some are very small. They're different stages, and I'm sure like in 2 years it's gonna look very different. And I'm gonna have to have more categories.
All right. No, thanks a lot. My other question is on involvement of other stakeholders. In my part of the world, quantum as a domain is something that's quite new, and trying to explain it to a number of people is quite extreme sport. And also trying to conscientize possibly people like other policymakers is quite hard. I just want to understand from your own experience in your part of the world, how did you manage to do it?
Yes, so it is still very difficult. There's still there's a lot of hype and misunderstanding about quantum. People they're not honest, and they promise things that just have nothing to do with quantum. What I can say is that there is an interest in. There's a lot of big countries that realize it's going to be a very a big technology. It's going to change a lot of things. So the usual big players like the United States, Europe, China, they have invested a lot of money into this, and this is because of because they see that it's going to be groundbreaking technology, and they want to a big part of it. They realize it's going to be a major thing in computing. So it was really they did it really for geopolitical reasons and so on. However, with that said, as you have proof of concepts of ideas and so on, software and so on that you can run on existing hardwares, then I'm sure that it's going to be much easier to sell for other countries. Like, for example, when I'm from Puerto Rico, there's no quantum startups there. Like it's just a small country that doesn't have a big research budget. However, so I'm in another country now working on that. And so but the idea will be that at some point we have practicality that will convince value of this. We're not there yet, of course. Like right now, it's because it's such a long-term view, and it's costly. It is difficult to justify a politician that maybe the horizon is just like 6 months or the next election. It might be a bit difficult to do the long term. But I'm just being honest and trying to explain what are the reasonable things. And of course, you can always contribute in an open source community and really push things forward. And when the solution is there, when you have the solution there, that will speak for its own. Yeah.
All right. No, thanks a lot. I appreciate it. And please keep it up. I like your presentation. It was very simple, nothing technical. Well, by technical, I mean physics. But thanks a lot. Just keep it up.
So I realized that people don't like physics. Sorry for that. We've been torturing people with physics on the platform. Thanks, César, for coming through. So anyway, thank you very much, everyone. I've shared the link to a cocktail that we usually host after these meetings to allow you to have one-on-one conversations with César and many of the other people who were part of this meeting. If there are no other questions, I think we can call this meeting, we can call it off, and let's meet in the cocktail. I shared the link. Be patient. It takes a bit of time sometimes to log you in and to match you with other participants. But well, all the best with what you guys are on. Thank you very much for coming through for this meeting. And thank you very much, César, for making this possible.
Bye.
All right. Bye-bye, everyone.